Welcome to the last JQI seminar of the 2021-2022 academic year. Very appreciative to Alicia Kalar and Kartik Srinivasan for helping to organize this. We haven't had a single, well, maybe we had one speaker that wasn't able to attend, and we've been able to do most of these live. So let's hope that we return to the previous mode with the lunch afterwards, or able to do that the following year. Meantime, for our last seminar, we're featuring, as we do every semester, 2 half-hour presentations by JQI postdocs. Andrey Grankin will start, followed by Aditya Sharma. Andrey was a graduate of Lomonosov State University in Moscow and the School of the Institut d'Optique in France, a postdoc at University of Innsbruck, and it's currently co-supervised by Viktor Galitsky and Mohammad Hafezi, neither of whom could be here at this very moment for quite different reasons. And so, Andrey, please take it away. It's 25 minutes for presentation, 5 for questions, and I'll give you a 5-minute warning. 20 minutes, which will be 11:30.
Okay. So, hello everyone. The topic of my talk today is enhancement of superconductivity with external phonon squeezing. So, conventionally, when we kind of talk about superconductivity, it's considered to be mediated by phonons, which are like quanta of lattice vibrations. And it has long been known that these lattice vibrations sort of mediate attractive interactions between electrons, as opposed to direct interaction, which is a repulsive, which is Coulomb interaction. And since we now have attractive interaction between electrons, they can form bound states, or is known as Cooper pairs. And since bound states are bosons, they can condense, forming a Einstein condensate, which exhibits all the interesting phenomena like superfluidity and so on. And in all this consideration, typically the phonons are assumed to be in some kind of equilibrium thermal state or in the ground state and so on. So it's an old story. But quite recently, it has been experimentally demonstrated that a non-equilibrium like excitation of the infrared active phonon mode in a solid can significantly enhance the superconductivity, which is happening in this material, which is here. It's a bulky ball, K3C60. And so essentially what has been shown is that the physics, the conductivity and reflectivity of material with driving is at high temperature is very similar to the situation when there's no driving at low temperature. And in both cases, one observes the like superconducting like features inside of material, so which is shown in these blue dashed regions here on both figures. So essentially, the main message of this slide is that one can sort of drive the system to some non-equilibrium state, and in this non-equilibrium state, the material can exhibit certain superconducting features. And so essentially, there has been several conjectures that this enhancement of superconductivity in this high temperature non-equilibrium state might be related to so-called squeezing of phonons inside of this K3C60 material. So let me just briefly introduce various general concepts of phonons inside of solids. So typically, the simplest toy model of phonons is basically if we consider just atoms which are connected by springs, and the restoring force for each atom is sort of proportional to the distance between each ion. And in this case, so for a really simplistic toy model, the spectrum of vibrations inside of such lattice has several bands so this is a situation when we have different masses of atoms. And in this case, we have two different kind of branches. So here we have acoustic branch and the optical branch. So acoustic is kind of reminiscent of Goldstone modes inside of the solid. And in the limiting case, if we assume that the curvature of the phonon mode is sort of 0, we can consider an extremely simplistic model, which is called the Einstein phonon model, is when there's completely no dispersion of the optical mode. And in this case, each ion's vibration is represented just by local excitation of the motion of each atom. So in this case, we can just simply consider a kind of a wave function of this or a density matrix of this atom, which can be either in the ground state or in a certain equilibrium state, but overall it's just represented by a certain harmonic oscillator. And the question that one may ask, so what is happening if we now externally drive this system with the laser field? And one of the interesting scenarios are realized when we consider a so-called squeezing of the oscillator, which is represented by this Hamiltonian. So that's basically a dagger plus a dagger squared. And so in my talk, I will explain why squeezing of optical or just squeezing of a mediator of interaction, why is it helpful to enhance interactions between electrons. So there's been several proposals along these lines from several groups. So here I highlighted several of them. So first is proposals from Eugene Demler's group, and second from Andrew Midas's group, and they differ. So they're kind of similar, but they differ in kind of underlying idea where the squeezing of phonon degree of freedom comes from. So essentially, so I first focus on the first two proposals. So in both of them, what is considered is that the external laser driving excites the infrared active optical phonon mode inside of the solid, and it's basically so given that the material is quite nonlinear from the phonon point of view, what can happen, and this process is shown to be allowed, is that infrared active optical phonon mode, it can kind of undergo spontaneous parametric down conversion like process, and it will basically decay into a pair of acoustic phonons. And so this process is known like multimode squeezing in optics, and I will present more a bit on this later. So in my talk, I will address why is it kind of useful and why it helps superconductivity to have this kind of process. So in a second proposal by Andrew Midas's group, so the contribution from acoustic phonon from this lower branch is neglected, and only the optical phonon mode is considered. And due to the symmetry in the system, it is known that this optical phonon mode is interacting with electrons in a nonlinear way, such that square of the displacement of each phonon sort of interacts with electron density. So this is due to the parity symmetry in the system. And what you can do is simply expand the square of the displacement operator of each ion in creation and annihilation operator of phonon modes. And this is already clearly, it has some squeezing contribution to the interaction. So it's been conjectured in this paper that this kind of squeezing is useful for superconductivity. And it's clear from this expression that in this case, the squeezing is proportional to the electron density, and therefore is sort of limited by the interaction strength inside of material. So in my talk, I will explore this kind of configuration of the system, but now I assume that in addition to this electron-induced squeezing, we consider that we can squeeze the phonons with some external way that I will explain on the later slides. But so before proceeding to the calculation, let me briefly explain why squeezing like useful at all for superconductivity or electron interactions. So consider a simplistic model of so-called parametric amplifier. So this is harmonic oscillator with a squeezing term. And so let's now just do a simple exercise and write the Heisenberg equations of motion for that kind of system. So this is a linear system, so the equations of motions are linear. And what we can do, we can solve them by in a trivial way. And then what we can do, we can consider, for example, correlation function of such a degree of freedom of different quadratures, for example, of X or P quadrature of such an oscillator. And so basically, if we do this exercise, what we find is that in the static limit, the interaction, which is mediated by this kind of degree of freedom, is has kind of interesting properties, that it can be enhanced or the opposite, like it can be reduced, the interaction strength, depending on the magnitude and the sign of this the parametric driving strength. And essentially, so in order to enhance, obviously in this model Xi should be negative, and in this case the interaction, which is mediated by this degree of freedom, will be magnified. So let me now proceed to the main part of my talk. So first I will introduce a model, and I'll provide an analytical solution of that model of non-equilibrium driving of a phonon degree of freedom and the superconductivity in that kind of system. Then I'll proceed to the numerical results in comparison with the analytical solution. And finally, I will conclude with some experimental considerations for the implementation of the model that I will introduce. So as I discussed before, so we now consider the Einstein phonon mode. So essentially all it's like independent vibrations of each atom inside of the lattice. And what we now consider is the additional external laser driving. So this driving has several contributions. First of all, the regular linear driving, which is simply like dipole-dipole interaction with the light field. And so this is a regular infrared optics of the phonon mode. And the second ingredient is the additional one, which I consider in my talk. So this is the additional parametric excitation of the phonon mode. And as I discussed before, the optical phonon mode interacts quadratically with the electron density. So here's the interaction term. So now, avoiding many technical details, what we do, we first transform into the displaced and interaction frame with respect to laser driving frequency omega p. And doing the RWA, the rotating wave approximation, we arrive at a very simplistic Hamiltonian, which is written here. So what we observe is a kind of harmonic oscillator in a frame with respect to the probe frequency. So it has additional squeezing-like term, which I explained previously. And we have usual linear-like interaction of phonon degree of freedom and the electron density. So here it's linear because it's essentially linearized because we drive to a certain displacement. So it's now convenient to perform certain transformation of this Hamiltonian, which is called the Bogoliubov transformation. So essentially, let's consider only the phonon part. It's quadratic, but it can now be diagonalized in the creation and annihilation basis. And this can be done by the conventional Bogoliubov transformation, which mixes creation and annihilation operators into a new operator. And essentially, if we now use this new basis of states, which can be called squeezed basis, we can diagonalize the free evolution of the phonon part. And what we get in the end is a Holstein-like interaction model of electrons and phonons in a non-equilibrium state, where what we observe is that the coupling to phonons is sort of exponentially enhanced due to the squeezing. But at the same time, the detuning from the resonance is sort of decreased in the presence of squeezing. And so we have two competing effects. First is the exponential enhancement, but at the same time, the oscillator has lower energy. And as I will show in the following, so these two effects will kind of compete in determination of the transition temperature, for example, in such a gas. So how am I doing in time?
You have 12 minutes remaining for the talk, plus 5.
Okay. So yeah, so then we start with this kind of model. So this is the usual Holstein model. And so what we do, we apply the conventional Migdal-Ellsberg theory to the system. So Migdal-Ellsberg theory is essentially a fully renormalized field theory for electron and for phonon propagator. So it's a self-consistent solution for both electronic degree of freedom and phonon degree of freedom. So this is an integral equation which can be solved numerically, and then based on the solution for the self-energies for electron and for phonons, what we can do, we can solve a Ellsberg equation, which is a gap equation, kind of generalized a BCS kind of equation for determining the transition temperature. When this equation has solution, it implies that the system undergoes transition to a superconducting state. So we solve this equation. So I will not go deeper into these details. And what we find is the following expression. So we find a certain analytical estimate for the transition temperature, but it involves several parameters of this effective Holstein model that I just briefly introduced. So first of all, it's the effective coupling strength parameter, which is exponentially enhanced, as I discussed. Then due to the interaction with the phonons, this bare electron phonon coupling gets renormalized in a conventional way. So it kind of is enhanced by the strength of the interaction. And then the transition temperature takes the BCS-like form with the effective electron-phonon coupling strength, and the frequency, which is in front of this TC, is given by the following expression. So this involves both the coupling strength of electron gas to phonons and also the driving, detuning, and squeezing terms. So first of all, what can be observed is that this expression does not make sense in certain regimes. So for example, when the expression inside of the square root becomes, for example, negative. And as I'll explain, this is a signature of certain lattice instabilities in the system, which are caused by driving. So let me just briefly go over what kind of instabilities we observe that are caused by driving. And these instabilities are not superconducting instability. This is something else. So first of all, what we see is that when the electron-phonon coupling strength is very large, the frequency sort of becomes complex. And in this case, this is well known that if the coupling strength is very strong, the system undergoes Peierls instability, and so essentially it's another state of phonons, which is which also induces a finite gap for electron degrees of system, and so electrons become essentially an insulator. So this is a bad regime. And second instability is when this I'm sorry, should be the opposite sign. And it's when the squeezing is stronger than the effective detuning from the oscillator energy. So this is conventional parametric instability in our systems. It occurs because we have both regular driving and parametric driving, and at some point we hit the parametric resonance inside of the system, and then the phonon occupation grows exponentially, and this is also the regime that we want to avoid. So in the following, all the parameters that we consider will be lying outside of the regimes of these both instabilities. So let me now compare the analytical estimate that we just obtained with the numerical solution. So here is the result, and let me just briefly go over what is shown on this figure. So let's first consider the situation when there is no squeezing. So this is shown with this blue curve. And what is observed is that at lower detuning, the essentially the transition temperature is increased. And this is it's happening mostly because the interaction strength is inversely proportional to the detuning from phonon resonance. Now, if we turn on the squeezing, what we see is that this resonance is kind of shifted, and the maxima of all curves are shifted from 0 depending on the squeezing strength. In fact, it's possible to find the optimal solution of the critical temperature as function of the squeezing strength. And it can be shown that it scales as square root of the squeezing. And the optimal detuning in each case is given by this simple expression. And it also kind of displays the fact that at lower detuning, we will hit one of the possible instabilities of the system, which are not superconducting instabilities. And this regime is not of the interest in this case. So here in this figure, we fixed the linear driving, which we also had in the system, and we only scanned the parametric driving, which is given by this D. So if we now scan both of the drivings, the linear and parametric one, we get the following curve, which is sort of similar to the previous one. So in this case, what we can see that in all cases, the strongest transition temperature to superconducting state is sort of on the boundary with the instability towards the charge density wave. And in all cases, the driving strength, the linear and the parametric driving strength, they both push the system towards the charge density wave instability. So let me now proceed to the experimental considerations, how the model that I just described can be implemented in the system. So first of all, let me briefly go through the various terms in the model that we consider. So it's linear driving, the regular one, the parametric driving, and the electron-phonon quadratic interaction. So let me start with the last term. It's the simplest one. So it is quadratic electron-phonon coupling. And in fact, it is just known that in certain materials, like 3C60, it is quadratic by just symmetry arguments. So, and another another situation where the coupling of electrons to phonons is quadratic in phonon displacement is realized in, for example, in graphene, where the out of plane phonons, they are also coupled quadratically to electrons, again, due to the symmetry reasons. So now let me discuss how the second, the most complicated term can be realized in this system. So this is the external parametric driving. So the first proposal how to perform the parametric driving of phonons has been done by a group of Andrey Grankin, and it has been shown that in certain materials, the coupling, so there is a nonlinear, so in addition to regular infrared active phonon mode, which is dipole, which has finite dipole, and therefore it's linearly coupled to light, there's also an additional higher order term, which is quadratic in the phonon displacement. So in certain materials, like 3C60, I think it's just inbuilt inside of the materials. And therefore, this parametric driving is already there, sort of. And the second proposal, how to induce squeezing of phonon degree of freedom, has been theoretically proposed by a group of Agrawal. And the idea in this case is that the squeezing can be transferred from optical degree to the phonon degree of freedom. So in this case, one assumes a cavity which has parametric down converter, which is classically driven, and the light inside of the cavity also interacts with the phonons inside of the material. And it has been shown is if one eliminates adiabatically the cavity degree of freedom, then one gets an effective parametric driving of the phonon degree of freedom. So we took the parameters from the group of Cavalieri. So this is just a list of all the parameters, and we ran our simulation. And what we find is that for a fixed driving strength, the squeezing helps so here we optimize over all parameters, and what we find is that additional parametric excitation helps to enhance the transition temperature around 2 times. And this is also shown to be correlated with the amount of squeezing that we have inside of the Phonon degree of freedom. So let me now proceed to the conclusions of my talk. So we considered how the external squeezing can help the electron pairing. So this is this enhancement in our model is allowed due to the type of decoupling of electrons to the phonons that we have in our system. And what we find is that the strongest enhancement is on the boundary of charge density wave instability. And another interesting direction that I find is that there is a way to decouple electrons from certain phonon degrees of freedom just by tuning the phase of the lasers. So thank you.
Thanks very much, and thanks for leaving time for questions. Who would like to start? Steve.
So on your very first slide with the experimental result of the K3C60, I noticed the first word in the title was possible.
Yeah.
So what's the thing about how experimentally solid this is?
Yeah, I think it has been. Yeah, I know that there are a lot of theories actually that explain these results. So I'm not aware of any experimental results that kind of repeat the same experiment. But theoretically, it has been proposed that it may not necessarily be connected to superconductivity at all. It might be some other exotic, highly excited states that can exhibit Meissner-like effects. But so it's kind of. I think it's kind of debatable.
Yes.
You talked about TC here. How is that defined? Is
Yeah.
that like with the gap equation, or is that?
Yeah. So here was.
You can repeat the question for people that are listening.
Yeah. So the question was, why do we consider that we have certain transition temperature in non-equilibrium setting? Yeah, so here we assume that electrons do kind of thermalize and approach some certain thermal-like state, simply because the interaction is usual Holstein-like interaction. But for us, it's more like the estimate of just pairing strength. So TC is just the strength of the interaction.
I have a two-part question. The first is a short one. For your parametric amplifier term, I think it was in the Hamiltonian in the other slide. Am I assuming that this is a real positive number?
No, not necessarily. So it can, in principle, be a complex number because it's essentially proportional to the phase of the laser that induces this parametric driving. Okay. And so I skipped a little bit this part, but the possible phase difference can also play a certain role.
And the second is that graph toward the end of the modeling where you showed the transition between the enhancement and the CDW instability. Is that boundary discontinuous? Or is it just very rapidly declining as you get into the CDW?
Yeah, so here, okay. So you're talking about this contour plot with the, so essentially the boundary is actually very rapid. So there is an exact point where it undergoes the transition. So, and this is characterized by the effective electron-phonon coupling to be some numerical number, which is approximately 0.4 with some other digits. Yeah, and this has been confirmed in the other settings, so that this is kind of what is happening. If this interaction strength is too strong, then the system simply.
I have a question for the room.
Imagine instead of the Elyashrik equation, we use the normal BCS equations. Do we still see any enhancement in the TC?
Yeah. Yeah. So in this case, we will get the wrong answer. So here it's very important that we have both. It's very important that we keep track of the retardation effects inside of the Phonon degree of freedom. Because so if I ignore the retardation, what is left is only exponential enhancement of coupling. But the retardation effects do not allow for exponential enhancement of TC. It's because essentially, so where is the analytical expression? Yeah, essentially this happens because there is this prefactor in front of this BCS-like expression, which gets modified by the interaction strength and by the squeezing itself.
BCS drops this one and just.
Well, yeah, BCS doesn't know what it should be.
Yes.
How did you arrive at the vector temporal?
You mean?
Repeat the question, basically.
Yeah, I could not hear it. Sorry.
Arrive at the vector temporal.
Okay, so this is so we have linear and parametric driving, and what we do first, we consider a displaced frame, which is displaced from like vacuum degree from vacuum state by the amount of like average coherence that is induced by external driving, and then we go into the rotating frame with the probe frequency. And then we do just the high frequency expansion of the resultant. So this is like low energy Hamiltonian that system is.
So your equation here is the key to the basic understanding of the phenomenon. It's a change in the electron-phonon coupling
Yes.
within the same band, existing band structure.
Yes.
Condensed matter
Yes.
environment. Is there a way that can turn a non-superconductor into a superconductor under realistic circumstances?
Yes, so we found enhancement beyond the equilibrium, like transition temperatures. So this external driving can enhance superconducting state in principle.
Okay, I think let's thank. The next speaker will be introduced by Alan Middahl.
We have Aditya Sharma, who got his bachelor's at Cornell in applied and engineering physics. He got a master's at University of Illinois in Urbana and did his PhD under Paul Kwiat, looking for photonic bound entanglement using hyperentanglement to study mixed entangled systems. And he has experience with fused silica waveguides and quantum interactions therein.
So your drive should have appeared down here. We'll be starting the presentation shortly. Okay, so you need to clip that on.
We see the correct slide in the right view.
Laser pointer forward, back.
Okay.
Same rules as before, 25 plus 5.
Sounds good.
Okay, so thanks for the introduction. I'm going to talk about some work that I actually started at University of Illinois, but it kind of got cut off by the pandemic a little bit. So we're just wrapping it up, and I thought I could talk about it today. So in general, it's quite well known. I think that correlations can enhance metrological precision. They can be useful for various metrology applications. And today, I'm going to talk about beam displacement measurements. And in particular, we'll talk about split detection. So beam displacement measurements are useful for a variety of applications. For example, in atomic force microscopy, you can use it to detect the deflection of a cantilever. And basically, the idea is that you have a split detector, a detector with a left and a right half, and you can take the different signal divided by the sum signal, and that should be proportional to the displacement of the beam. And so in this kind of a scheme, each photon that hits your detector gives you a bit of information. So of course, you can just increase the number of photons you use a brighter beam, and that will give you more bits of information. For many applications, that's great, and you can do that. But if you're trying to minimize the number of bits that you use, if you're trying to optimize the number of photons that you use, then you basically have a trade-off. You can use your one bit of information to improve the precision of your measurement, and you could do that with a narrow beam, or you could use a wider beam and improve the dynamic range of the measurement. So you might ask, well, is it possible to get high precision using a large beam? And most likely you would think no, because these seem to be the two options. Well, you could try using correlated photon pairs. So this is a proposal from 2016 where we use spontaneous parametric down conversion, produce a pair of correlated photons, correlated in position, and separate them at a polarizing beam splitter. And then because of the correlations, maybe you can improve your precision of split detection. And the way that you estimate the position of the beam in this case is using this estimator. You take the number of coincidence events in which both photons hit the left side, subtracted from the number of events where they both hit the right side, and then divide by the total number of events. So essentially what you're doing is you're calculating the mean position of the two photons. If they're both on the same side, you get a 1, but if they're on opposite sides, they cancel out. So first of all, I guess it should be pretty obvious that this will not really improve things if you have uncorrelated photons. Because when you have uncorrelated photons and you use a regular split detector, what you're doing is you're averaging the positions of each that each event indicates. Another way to see that is to look at the joint position intensity of the two photons. So in this diagram, you see something that looks like a beam, but throughout this talk, anytime you see something that looks like a beam like that, actually what I'm plotting on the horizontal axis is the horizontal coordinate of one beam, and on the vertical axis is the horizontal coordinate of the other beam. So that's the joint position intensity in just a horizontal direction for the two photons. So now if you have a displacement in the positive direction, that joint position intensity will translate in the plus 45-degree direction. Because the width of that circular distribution is the same as the width of the one-dimensional distributions, you don't expect to see any difference if you have an uncorrelated pair. Now, if you had a pair of correlated photons, maybe that could work better, because now this distribution can have an elliptical shape. And since the distribution is translated in this plus 45-degree direction, the relevant width of the distribution is actually this narrow distance here. And the width of the photon itself, if I look at its marginal distribution, it's actually the same as before. It's still this wide width. So it's possible to do better with correlated photons. So before going further, I want to define a few things. So first of all, a quantity, well, first of all, an estimator. So an estimator is just some formula for estimating the value of an unknown parameter based on data that you have. And if we want to quantify how good that estimator is, we can use something called Fisher information. I'll just call it I of D, which is the amount of information that the data that you have could in principle give you about the unknown parameter D. And in general, that's going to involve some sort of sum over all the possible measurement outcomes that you could get. So for example, if you had that uncorrelated photon distribution, and let's say you had perfect detectors, so perfect resolution, so you could actually tell exactly, you could distinguish exactly which positions the two photons were detected at, you would integrate over all possible positions that you could have seen the photon, and it involves the probability of that occurrence, and also the derivative of that probability with respect to the distance that you're trying to measure. In split detection, you're sort of in the opposite limit. You have the most minimal resolution you could possibly have. You only have two possibilities. And so you only have to sum over those two outcomes. And of course, there are two photons, so there are 4 different outcomes you're actually summing over. So the significance of this quantity, I of D, is it tells you the inverse of that value tells you the lower bound on the variance of any estimator you could possibly come up with for this parameter D. So if we want to think about how good split detection is in general, it turns out it's actually really good for measuring small displacements. So if we assume that the joint position intensity we're looking at is Gaussian, then in this short dimension, we say it has a width epsilon, and in the long dimension, let's say it has a width sigma. For the cases where the two photons are uncorrelated, the perfect resolution result scales as 1 over the variance of the beam itself. And you do about the same with split detection. So in the third row here, we're looking at the case where you have correlated photons. And there you see actually there's a change in the scaling. So in the perfect resolution case, you're actually doing as well as you would with a very narrow distribution, a very small distribution for uncorrelated photons. And in the split detection case, you actually scale less well, but you're scaling better than you do for given how wide the photon is, because the width of the photon is actually sigma wide. And on the right side here, I'm plotting what I of D looks like, not just for very small displacements, but also for larger ones. And the key takeaway here is that although the asymptote for very small displacements is not as good as it would be for a narrow distribution, the dynamic range is much better because it falls off more slowly because the distribution is wide. It has some width to it. Okay, so with that, we'll look at the experimental setup. We use spontaneous parametric down conversion to make pairs of correlated photons. In particular, we use type 2 collinear down conversion. So the two photons that are produced have opposite polarization. And the pairs that are produced are naturally entangled in their position because they can be produced anywhere in the pump beam. And in this case, that pump beam width is 500 microns, but they also have to be produced in the same place. And the crystal thickness determines the uncertainty on that parameter. So in this case, that's 24 microns. And so we observe joint position intensity, something like that. One thing you might notice in this image is that the joint position intensity is actually correlated. So it's along the 45-degree line. And everything I've been showing you so far is along the minus 45-degree line. So that's actually a problem for the scheme that I was showing earlier. So when we do want to actually do this experiment, it's important to flip the JPI. So you start off with a correlated distribution. You split up the photons with a polarizing beam splitter, and one of them takes 1-2 reflections before it gets to this moving mirror that's being probed. And the other one takes 1, 2, sorry, I counted wrong. 1, 2, 3 for one of them. And for the one that goes straight through the PBS, it gets 1, 2 reflections before getting to the moving mirror. So basically the parity of the reflections is different. And so you flip the JPI as a result. It's also important that we 4F image here the distribution at the crystal onto the mirror, because due to the very narrow width in the narrow separation of the photons, as that joint position intensity propagates, it will also diverge just like a regular beam.
Sorry, what is this 4F image?
Oh, 4F imaging just means, so we have the crystal distance to this lens is F, one focal length, and then we propagate to the next lens, which is another F. Yeah. Okay, and so yeah, the focal plane for that 4F imaging is the detection system. So by the time you reach the detection system, you're back to what you had at the crystal. And at that point, we can either use scanning slits to make a measurement like the one I showed earlier of the JPI, or you can swap those out and put in D-shaped mirrors, which pick off the beam and allow half of it to go to one detector, send half to the other. And you can effectively realize a split detector that way. Okay, so given this setup, we can try to actually measure some pre-calibrated displacements of the mirror. And so this is an example of what we see. Now, because of the details of the setup, you know, all of the theory that was done for this involves Gaussian beams. It involves a lot of assumptions which actually are not valid for this setup. So we cannot actually compare our data directly to the theory. Instead, what we do is we Monte Carlo simulate what would happen given the JPI that we measured. And so the colored curves that you see are actually Monte Carlo simulations, and the error bars on those are the variance that you would see on those quantities, because we're actually simulating what we do in the experiment. So on the left is the mean of the estimator that we saw earlier, where you just average the positions of the two photons. For each measurement, the idea is that we calculate the estimator using about 850 photons, and then we do that repeatedly, and so that we can calculate a variance. And we can use a Monte Carlo simulation to model the whole thing. So here you can see the variance curve, which is, again, related to 1 over the Fisher information. So the key point here is that, as expected, we see that the estimator variance close to 0 is consistent with this correlated joint position intensity, and it beats the case where you had an uncorrelated large beam. Now, there's this detail of in the estimator mean. You would expect, of course, the estimator mean should. Okay, the estimator mean should just be a straight line because it should tell you exactly where the mirror is. But that kink is actually due to details of the D-shaped mirror, and you know, it's perhaps not surprising that at the edge something weird happens, but yeah, the D-shaped mirror is not optimal at the edge, and it's actually not optimal in a rather strange way. So it seems to depend on the wave vectors that are entering the mirror. Okay, so given that result, you know, we can try to do better because, as I said earlier, this correlated beam does well for split detection, but it should actually be just as good as a very small beam if you have perfect resolution. Unfortunately, we didn't have multi-cell detectors, so instead we have to go back to scanning slits. And what we do is actually we just scan, we can scan the slit, do a slit scan at various displacements of the mirror and just simulate what would happen if we had an M-pixel detector. And you have to calculate this kind of estimator, which involves the probability at each pixel at 0 displacement and also the derivative of that probability. So you can compare what happens with Monte Carlo simulations of those experiments with the Gaussian inverse Fisher information. And you see that there's a pretty close match. The main interesting thing here, though, is that actually it doesn't consistently get smaller, right? So there are some weird places like at 3 pixels where you suddenly see a spike. So that's perhaps not too important, but if you look into it, there's something that may be to be gained here. So the point is that if you look at the intensity of the Gaussian beam, it's just not at all distributed the right way to use 3 pixels, right? So if we think about how we might change that, this long dimension of the JPI is determined by the pump beam width. And if we simply do a mode conversion on that, so if we just apply a pi phase shift to 1/2 of the beam, we can get a distribution that's more favorable for using 3 pixels. So with this, you can repeat the measurement, and you can see that now we've sort of fixed that curve, and now for 3 pixels, you actually do quite well. Okay, so to summarize, what we've talked about today is that we can exceed the usual precision limits for split detection and generally for beam position measurement using correlated photons. And in the perfect resolution limit, they actually match photons that have the width equal to their correlation distance. And for a given pixel number, we might actually be able to improve the precision of our measurements by tailoring the joint position intensity. And finally, the last 2 things are things I haven't talked about yet. So you'll notice actually I barely mentioned the word entanglement in the whole talk, and that's because while it's true that the photons were entangled, it actually was not important. All the pictures that I showed were just intensities, and actually that was the only important feature. So that's, I think, an interesting aspect of this particular measurement. And finally, the main application of this, I think, is that by keeping the incident intensity constant, you can actually improve the measurement precision. So you might be able to use this in some applications where you want to sample a bigger area actually and still get a precise measurement. So I want to thank my colleagues from the lab and also theory, and that's it.
Thank you. Plenty of time for questions. We'd like to start.
I've got one, Charles.
Go ahead.
So with the split cell detection, I thought one of the results was you're better off not splitting a detector so that you catch 1/2 and 1/2, but you're actually better splitting where you get sort of like the outer third or quarter on the two sides and actually ignore the part in the center to get better signal to noise. Does this relate to that at all?
I'm not familiar with that result, actually.
Because where you show your Gaussian, the side of the Gaussian is where you get the most sensitivity. And you can certainly imagine that the central part of the beam doesn't add much information and in fact just makes for more noise.
So the information is highest at the center. And yeah, I guess, okay, so if we just think about this, this formula in particular. So if, and I've actually left something out here. So this is, it should actually be the derivative of the logarithm, not the derivative of the probability. So that, I guess I'll have to get back to you on that. I'm not sure.
Okay, all right.
Yep.
That's fair.
Yeah.
Yes. How important are aperture effects here? So you're talking about the mirror kind of flipping. Like, does the size of the lens have an effect? Since you have such a tight distribution, if you like, presumably kind of scatter. So if you have two small lenses, you might lose the
Yeah, that's really important. So the 4F imaging stuff I was talking about, that's the reason it's important, because this beam will diverge very fast. And then if you let that happen, by the time you get it, you've all the information is gone, right? So yeah, so the apertures are important, and this had to be designed such that you don't clip, basically.
So you see an improvement for a case of perfectly correlated photons. What about the case if you just say, well, we have a second order correlation function, G2, and we look at is there, by varying that correlation function, is it possible to see an improvement in resolution before you reach this, the perfectly correlated photon limit?
I didn't quite understand, I think. So I guess you can vary the degree of correlation in the sense that I'm just looking for a good picture. So yeah, so I can vary the ratio of those two widths, and that is in some sense varying. I mean, that's varying the amount of correlation.
Yes.
Right? So yeah, you see an improvement immediately, right? Because effectively, this 4/sigma-epsilon will be a little bit larger than 4/sigma squared.
Anyone else?
Yeah, so Aditya, did you ever look at the minimum efficiency you need for this to be a win, in the SPDC?
Oh, the minimum detection efficiency?
Or conversion efficiency from the pump to the down converted photons.
Oh, I don't think that matters, because all you care about here, the idea is that you want to get as much information per photon out. So you're not trying to get a lot of flux. In fact, the idea is probably that you don't want a lot of flux. Because if you did, then you could just use a lot of light. One issue, though, is that you do need, I mean, for it to be practical, I guess you do need a high detection efficiency, because you're counting in coincidence. So if you lose one photon, you're lost basically. So it's important that you have high detection.
But you don't, I mean, you didn't compare it to just using the beam and not having the BBO crystal at all?
Well, that's actually what I think that would be equivalent to this comparison here, where you're looking at uncorrelated photons.
Right.
Because when you have uncorrelated photons, the split detection measurement, the 2-photon measurement, actually gives you the same precision as just treating them independently.
Mm-hmm.
It's just worse because you also have to detect them in coincidence, so you're effectively going to do worse.
Mm-hmm.
Did that answer it?
Yeah, that's it. We can talk about it later.
Okay.
I guess there's a similar question. Did you see the effect of squeezing on the uncorrelated versus correlated to see the improvement in the?
So do you mean this plot?
I guess, I mean, this is a theory curve for the expectation, but I mean, like in the
This is actually yeah, sure. In the experiment, oh, did we do an experiment with uncorrelated photons? No, we didn't do it. No, we did not do that.
Anything else? Well, if not, let's give both speakers thanks.